Hi everyone, and welcome to chapter 3, technically 3.1, where we're going to cover probability topics. And in particular, this section has to deal with terminology. So it's going to be kind of like a vocab heavy today. So let me share with you really quickly the objectives of the chapter. So for chapter 3, we're going to talk about what is probability and understand and being able to use the terminology. Then we're going to talk about mutually exclusive events and independent events. And then we're going to talk about addition rule, multiplication rule, contingency tables, Venn diagrams, and then finally tree diagrams. So let's begin with terminology. Okay, so what is probability? Probability is something that we do all the time, but sometimes we're not even aware that we're using it. So probability is like a measure of how certain we are that something will happen, okay? So how certain we are that an outcome of a particular experiment or activity will be. So what's an experiment? So it's something that's planned, that's carried out under conditions that are controlled. If we don't know what the result will be, then we call this a chance experiment. So here's an example. An example of a chance experiment is flipping a fair coin twice. We don't know if we're going to get heads, tails, or both heads or both tails. We don't know that. So that's chance. Okay, so the result of an experiment is called an outcome. So this is really important. An outcome is a result of an experiment, okay? The sample space of an experiment is the set of all possible outcomes. So there are three ways to represent a sample space. Is either you can list all the possible outcomes, you create a tree diagram or a Venn diagram, okay? This capital S is used to denote the sample space. So let's say, for instance, when you flip a coin, the sample space S consists of either getting a heads, H for heads, or tails, right? There's only two possibilities when you flip a coin. I mean, really, those are the only two that we consider, right? Where H is heads and T tails are the outcomes. All right. So what's an event? An event is any combination of outcomes. So usually we denote events with uppercase letters like A or B. So let's say, for example, the experiment is to flip a coin, and we say that event A could be getting at most like one of them being heads, right? So the probability of an event A is written like this. We say this P of A. Now it's not P times A, it's P of A. It's probability of event occurring, okay? So recall relative frequency. So the probability of any outcome is a long-term relative frequency of that outcome. So let's say, for instance, how do we guess, what's the probability of getting a heads when you flip a coin? Well, that's 1 out of 2 outcomes, okay? And then I talk more about relative frequency. Let's see, we've talked about relative frequency where you count the number of times over the total possible frequencies. So let's say you flip a coin twice, you might not get 1 heads and 1 tails. You might get 2 heads or 2 tails, but if you were to flip a coin like 10,000 times or 20,000 times, about half of those times will be heads, okay? So that's the long-term relative frequency. So probabilities are always between 0 and 1 inclusive, meaning you can include 0 and you can include 1, but probability will never be negative and it will never be greater than 1, okay? So if the probability of A is 0, that means the event can never happen. If the probability is equal to 1, that means the event always happens. And if you have a probability of a 0.5 or 1/2, that means that the event is equal likely to occur or not to occur. And this is what I'm saying. So if you flip one fair coin repeatedly from 20 to 2,000 to 20,000 times, the relative frequency of heads approaches 1/2, which is the probability of heads. So it's equally likely. That means that each outcome of an experiment occurs with equal probability. So let's say, for example, when you flip a die, you have the dice have 6 faces, right? Each face is just as likely to occur as any other face, right? So the probability of getting a 1 would be 1 out of 6 total, right? Because there's total 6 outcomes. If you toss a fair coin, a head or a tail are equally likely to occur. If you randomly guess the answer to a true-false question, you are equally likely to get a correct or incorrect answer. Okay, so how do we calculate the probability of an event? Okay, so let's say if we want to calculate the probability of an event where all the outcomes are equally likely, we count the number of outcomes for event A, and then we divide that by the total number of outcomes in the sample space. Okay, so let's suppose we toss 2 coins, right? A dime and a nickel. And what are the possibilities? What are the total possible outcomes? Well, let's consider. We can have both be heads. Maybe the dime is tails and the nickel is heads. Or the dime is heads and the nickel is tails. Or both are tails. There are no other outcomes. So you have 4 possible outcomes, okay? Where T is tails and H is heads. So this sample space has 4 outcomes, okay? Let's suppose that the event is getting 1 heads, right? The only 2 events that fit this, 2 outcomes that meet this condition is this one, TH or HT. Okay, so there are 2 outcomes. Since they're all equally likely, the probability of A occurring is number of outcomes in event A divided by number of outcomes in sample space, which is 2 out of 4, which is 0.5 or 1/2. Okay, so let's say, for instance, you roll a die, fair 6-sided die, with the numbers 1 through 6 on its faces. Let's suppose that E, the event E, is rolling a number that is at least 5. So the only possible numbers are 1, 2, 3, 4, 5, 6. If you roll a number that's at least 5, that means it has to be 5 or 6. There are no other possibilities that are at least 5. Like there's not 7. There is no 2.8. There's no 6.8 on a die. It's just 1 through 6. Okay, so the probability of E happening is 2 outcomes out of a total of 6 outcomes. Okay, so if we were to roll the dice only a few times, you wouldn't be surprised if your observed results did not match the probability. Okay, so if you were to roll the die a very large number of times, you could expect that overall 2 out of 6 of the rolls would result in an outcome of at least 5. Okay, so you wouldn't expect exactly 2 out of 6, but the long-term relative frequency of obtaining this result will approach the theoretical probability of 2/6 as the numbers of repetition goes larger and larger. So the more that you do it, the closer to the theoretical probability you get. Okay. All right, let's see if we can do some of these. So let's do a super fun example. Let's suppose a jar of 150 jelly beans contains 22 red, 38 yellow, 20 green, 28 purple, 26 blue, and then the rest are orange. Okay, so let's go ahead and push pause and see if you can tell me what's the probability of getting a blue jelly bean, okay? Or the probability of getting a green jelly bean. What's the probability of getting an orange? What's the probability of getting a purple? What's the probability of getting a red? And what's the probability of getting a yellow? Okay, so I'll let you guys have a shot at that. Okay, I'll just give you 10 seconds to pause, write your answers down, and then come back to the video. Okay, so I'm gonna assume that you did pause it, okay, and that you tried it. So let's see if you were correct. If you had guessed for B, blue jelly beans, since there are 26 blue, if you guessed the probability of blue is 26 out of 150, you were correct. How many green are there? 20 out of, what's the probability of getting a green is 20 out of a possible 150 outcomes. Probability of getting an orange, well, you'd have to add all these up and subtract from 150. So that would be 16 out of 150. You get it purple, 28 out of 150. red 22 out of a total 150, yellows 38 out of 150. Okay, so what if you don't have outcomes that are equally likely? So that is possible where you have an outcome that's not equally likely. So let's say, for example, you might get a coin that is unfair or biased. Okay, so that does happen. So sometimes like an example would be two professors in Europe had their stats students test the euro coin and discovered that in 250 trials, a head was obtained 56% of the time and a tail was obtained 44% of the time. So that seems to imply the coin is not fair, but we would have to do more repetition to see if we were right about that or not. Okay, so some dice might be biased. If you look at the dice in the game that you have at home, usually the spots are small holes carved out and then painted. So your dice may or may not be biased. Sometimes the outcomes could be weight affected by the slight weight differences due to the different number of holes in the faces. So gambling casinos make a lot of money depending on outcomes from rolling dice. So casino dice are made differently to eliminate bias. Casino dice have flat faces. Their holes are completely filled with paint that has the same density as the material that the dice are made out of, so that each face is equally likely to occur. So later on, we will learn techniques to work with probabilities for events that are not equally likely. I just want to say that is a possibility. Okay. So let's do another example. So let's say here you have the probability that a particular knee surgery is successful is 85%. Let's find the probability that 2 knee surgeries were successful, okay? So what is our sample space? Okay, so what are all the possibilities that can happen? You can either have, if you have 2 surgeries, you can have either 2 successful ones, 1 successful, then 1 failure, 1 failure, and then 1 successful, and then 2 failures. But the probabilities of these events are not the same. So the answer to the question, what is the probability of 2 successes, is not 1 out of 4, only because they're not equally likely, okay? Because the probability of it being successful is higher than it being unsuccessful or failing, right? So we need to talk about other probability rules before we can discuss how to solve this. So let's continue. Okay, so we have 2 types of events. We have A or B and A and B. So sometimes the or is depicted by a U. I'm just gonna have to, sometimes, so when you say A or B, it's also written as A, sorry, this is an A, union, this is a U, B. Okay, this is like set theory. So A union B is one way. A and B is also depicted by this symbol, and it looks like an upside down U. Okay, that means and. So let me talk about what these 2 things mean. When you say an outcome is in A or B, means that the outcome could be in A or in B, or it could be in both A and B. So let's say, for instance, suppose A consists of the numbers 1, 2, 3, 4, 5, and B consists of 4, 5, 6, 7, 8. So then A or B, or A union B, would be everything is invited to the party. Okay, so an or a union, so union is the same thing as saying or, would just be everybody gets invited to the party. It's everybody except you don't have to list it twice. Okay, so it's just every single possible outcome is here, 1 through 8. Now, to be considered in the intersection, this is also called intersection and. So to define that, the outcome has to be in both A and B at the same time. So that's why I like the term intersection, because it's where these 2 sets intersect. So let's say A consists of the numbers 1, 2, 3, 4, 5. And let's say B consists of 4, 5, 6, 7, 8, like we did previously. Which 2 elements, right, or things in this set, which 2 are in both set A and set B? So you see 4 and 5 here, 4 and 5. So 4 and 5 are in both. They're in the intersection, or you could say A and B consists of 4 and 5, okay? All right, let's continue. Let's define complement. Complement can be denoted A prime, or sometimes people say not A. They call it not A. So really, it just means A prime means all the outcomes that are not in A. So let's say you have a sample space, and then you have your event A. And if you want to talk about A prime or not A, or the complement of A, those all mean the same thing. You're basically saying, okay, so let's say here's the sample space, and A consists of, so sample space consists of the numbers 1 through 6. And then A consists of 1, 2, 3, 4. So what are the elements in my sample space that are not in A? In other words, what is the complement of A? So it just depends on where you live, like what is your sample space and stuff like that. So not A or A prime would be, okay, so none of these. What's left are 5 and 6. So A prime is 5, 6. All right. Now, if I was to add these together, the probabilities, I would get everybody, because A and its complement, the union of those two is the whole sample space, okay? So the probability of A occurring is 4 out of 6. The probability of not A or the complement of A occurring is 2 outcomes out of 6 total. So if I add this two together, 4 out of 6 plus 2 out of 6, I get 1. Now it kind of is intuitive if you really think about it, because if you have like a sample space of all these outcomes, right? And a subset of these outcomes is A or B or what have you, well then everything else that's not in that is considered its complement. So of course, if you're going to add them together, you're going to get the entire sample space, which occurs is always going to occur 1 out of 1 time. Okay, so that's complement. All right, let's continue to talk about conditional probability. So basically, it's a probability with a condition. Okay, so it's kind of like your sample space gets restricted. Okay, so let me talk about what that means. So conditional probability has this straight up line, and the way that you read it is probability of A given, so this up and down line we say given B. So we say A given B, probability of this event occurring given that it under this condition. Okay, so we like kind of change the sample space. Okay, so probability of A given B is the probability that event A will occur given that B has already occurred. So what this is called a conditional, and that reduces your sample space, okay? Because we calculate the probability of A from the reduced sample space B. All right, and that's your super fun homework, and I will see you on the next video.